Hello and welcome back. This is the third part of our attempted repair of an HP8664A 3 GHz generator that we want to use as a backup transmitter for our Apollo.com setup. Initially, our flea market instrument was unable to get through initial calibration without a long delay and several errors, and has heavily distorted output in the two lower bands below 375 MHz. In part 1, we diagnosed the fault with the help of block diagrams, the only information available from HP, and narrowed it down to one of two modules. In part 2, we gave a clean bill of health to the LF driver. That left only the output amp module as faulty. Unfortunately, the fault could be in the proprietary HP Golden Box, a hybrid RF amp that is an Optanium. But it could also be caused by some of the bias or voltage controls around the hybrid. So we started debugging that first. And that's when we had a little accident. We heard a pop and the magic smoke came out. The fault was all ours, from a misconnected power connector, which put minus 15 volts on the 5 volt rail. The tantalum cap didn't like it and let the smoke escape. It was easy enough to replace the cap, but then we found out that not only had we lost the down converter stage, but that an unlevel red LED also came up. That led us to a long chase, which uncovered a dead quad analog switch chip. Hooray! After replacing the switch, we got our down converter back. But we still have our nagging unlevel LED, and if we can repair that, we need to get back to debugging the bias circuitry. Note that there was a bit of an upside to this clumsy incident. We spent quality time reverse engineering about half of the board, and we are starting to understand it better and better. It is no longer this intimidating monster of an RF board from when we started, and gives me enough courage to press on with the repair. Alright, so I have further progressed in my reverse engineering of the board, and it starts to make a little bit more sense, and at least I think I have identified where the major ICs are in the block diagram, kind of one to one. So we had the one that killed our down converter was U11, the chip we replaced. Interestingly, in the board, the chip was over here and it controls this part over there. So this is an auto-routed board. You can tell stuff is all over the place and makes no sense. We know we have two faults remaining. We have the unlevel and we have the original fault, which I think might be a bias problem. So I concentrated into trying to find where the unlevel circuitry is, and this is called actually an out of lock detector, but it's just unlevel. And finally I found out it's U7 is this comparator circuit. LM339 is this little guy, and there is a signal that comes in, goes to two comparators, one that compares if it's too high, one that compares if it's too low, and then it comes out here to a switch. Over here comes back, and then it goes into the little light over there. So I think I've nailed this one, and the comparator is right here. So this little chip, LM339. And curiously, as far as I can tell, everything looks good except the signal that goes in, and I wonder if the LM339 has a leak or something. So I don't know if it's the signal that comes in or if the LM339 is not working, so I need to devise an experiment to figure that out. I can start to try to make some measurements and between the good board and the bad board and find if my suspicion is correct. Yes, I forgot to mention in episode 2, Philip of EBTKS board fame came to the rescue with another broken HP8664A. His has another fault, actually even more difficult than mine, but his amplifier board seems to work fine, so I can compare his good board with my bad one. Off camera, I've made some measurements on the two chips I identified that could be of problem, U7 and U1. Our lock detector is this LM339, and I can tell clearly is different from the bad board and the good board. The good board, the input to the lock, exactly level detector, is 0. And you can see it compares to plus 47 millivolts and minus 47 millivolts, so that's where it should be. On mine that's broken, the input to it is 0.265, and therefore the little LED comes on. But it's very unclear to me why it's 0.265 volts here. I could not find anything that would drive it that high. So I'm going to lift the pins, this and this one, to make sure that the circuit does not bring that up to that voltage. If not, I have to find out in the complicated analog circuit where that comes from. Okay, so I don't know if you can tell, but I have lifted two pins, this fellow over here and this fellow over there, which are my two inputs. And I'm going to now measure the floating input signal from over here and make sure that the circuit is not influencing the signal, which is my suspicion. Actually, I can tell what's wrong with the circuit. The pin that's wrong is this guy. This guy is 12 volts. Should be 0, like this one. So yeah, that guy is just let go. 12 volts on the input pin. Okay, that's no good. Okay, looks like we have found a problem with our unleveled LED. The input of the comparator chip had a short that tied it to 12 volts. I thought at first that the measured level was a problem, but no, it's the shorted comparator input that fed backwards into the measurement circuit. I don't have one of these LM339 surface mount comparators in my collection, so we'll have to wait for a replacement part before we can go further. In the meantime, let's go back to our original problem, the bias circuitry that we were in the process of debugging before we had our magic smoke incident. The other circuit that I am suspicious of, I found two, and it would be the low band bias adjust, and that guy is tucked in half of U1. And the other half does the regulation. So U1 is over here, and half of it I think has to do with the bias point, and half of it has to do with the 7 volt regulation that powers the circuit. And you can also see that they have shown it kind of split here, so I think I'm tickling the right thing. And that guy on the board is over here, and it's also completely wonky. On the good unit, the output should be minus 2 volts. On mine it's 13. The inputs are no good either. On the good unit, the output changes if I change the pot, because there's an adjustment. So that's the original measurement I wanted to do before I zap the whole thing. So turn this pot, see if the bias changes, and on my unit it does not. I'm suspicious of this dual op amp. Okay, so next suspect chip is the op amp U1, which is responsible for the bias of the low band amplifier. And here I have wired myself up a little op amp tester. Here we go. Okay, is it good? Is it bad? This is good. This channel's good. This channel is good. I'll be darned. Okay, so there goes my theory that this op amp is bad. I might just replace it with another one just to be sure, but that doesn't seem to be the problem. So I put another op amp in there and I look at the bias control and it hasn't changed anything. It's still stuck at minus 13.6 volts. So it's not the op amp. However, I did another measurement on Philips' machine, now with another mindset. Pardon the sideways multimeter on Philips' machine. I'm going to do the same measurement on his machine. And first, I'm going to put it squarely in the low band below 375 megahertz. And you see the minus 2 volts. However, if I bring it above 375 megahertz, all of a sudden it's also minus 13.6 volts. And it changes right at the change between high band and low band at 375 megahertz. 374 minus 2, 375 minus 13. So I think I have to look in a completely different direction. My circuit works, but there's something in the control that's not switching it from low to high band. Okay, so I looked into it more and entangled my op amp circuit, and it's actually two halves that do two different things. One half is a power supply to give regulated 7.1 volts here, and just a standard power supply with a regulating transistor, and that's the big transistor that I was wondering what it was doing. Is this guy just brings the 10 volts down to 7.1, extremely well regulated. It's just stuck at 7.1 volts, perfect. The other half of the op amp is used for a circuit that does the bias control, and that's the one that's not working. But I am missing stuff because I don't see over here how it switches. There is a regulation loop that's obviously missing. So my guess is that there's something else that's digital that opens the regulation loop when it's in the high band and brings it to minus 13 volt, and that closes the regulation loop and brings it to minus 2 point something volts, controllable by this spot when it's in low band, and that's not happening on my machine. I have to reverse engineer more of the board and see a part of the board that I haven't seen yet. And also note that that's not in the diagram, right? It says nowhere that there is a switch between the two, but obviously there is. So more reverse engineering.
Much later.
Yay! I spent more quality time trying to reverse engineer the circuit over here. That's my double op amp. And I tried to reverse engineer over here. That's not it. That's a circuit that monitors the output power. There's view circuits over here, over there, that didn't do anything. And then eventually I went over here, not knowing what else to do, and I found my digital my digital command. It comes out of the comparator. It turns out it takes a digital input from the latch, and one of them toggles right at the band change, and then it goes into this circuit that goes into the golden box. So I think that's the switch. And you might think this is the circuit we already lifted 2 pins. You might think it's because the circuit is bad, but I think it's worse than that, because if I look at the input it has 0 volts, and it should be a TTL input going from 5 to 0. Doesn't budge a bit. So the question is this guy driving it high or low all the time and that IC is bad, or is this driving IC bad? And to know that, I removed yet one more pin from my LM339. There, this guy is now lifted and isolated. And I measured Q6 here, and I don't measure anything good. If I measure on my little latch, 3, 4, 5, which is the output that was supposed to toggle. It's shorted to the next pin, and you do the same thing on another chip, and it doesn't do it. So my guess is that the initial problem was over here. It's that bad chip. It's a latch and it's never switching. So I'll order that one, and I'll just got the replacement for the 339 surface mount, and we'll change that and see if we at least go back to the state we started with before I blew the thing up. Off we go, surface mount stuff. Ooh. I got it, but I also got the decoupling cap next door. Oh, okay. Okay, we fixed the unleveled. No, yes, no, we did not. Oh, dang it. Alright. Well, I need to wait for the other circuit to arrive.
Several days later.
Alright, so here is the new one. Okay, I've now changed 3 chips, the analog switch, the comparator, and the latch. We can try. Oh, light is not on anymore. No, it is on. Okay. Okay, however, I think we've made some progress. Let me demonstrate. Now the bias works. I can change the bias, and here we go. It's back to where it should be on the lower band, and the LED, level LED is good. So let's go to lower and lower frequencies. Oh, we might have repaired it. Okay. All right. Well, you know, we've done something. How low can it go? 0.1. Yeah, we have it down to 100 kilohertz. No errors. Let's see if it recalibrates. Okay, no cigar, still shows the same result code. So we're better, but we're not 100% good. It looks okay on the output, but it might not have. If I put it on the spectrum analyzer, it may still be distorted. So as before, it's beautiful above 375 megahertz. And here we go, we went to the 300 megahertz, and so I'm adjusting the amplifier bias, which I think is the voltage it's run at, and that's where it used to be, completely distorted, and now if I move it completely it's better, but it's probably not happy because I have only 30 dB to the last harmonics. See if we can vary it around here. So I'm back to my original thinking that something is wrong either with the bias generation or something inside the amplifier is degraded that requires us to move us very far out of bias. Whoa, we finally have meaningful and non-destructive progress. We changed 2 more chips and things are working a lot better. I'd say we are almost 100% back. If it were not for slightly too much higher harmonics in the low band according to the HP spec, we'd call it perfect. Still, I have to move the bias pot into an extreme position to get there, which isn't quite normal. So next stop, the golden box. And believe me, you are in for a treat. See you in the next episode. Woohoo! Success! Alright.